Hey guys, this is a revised video for Vogel's approximation method. In the original video, I had a slight error in the second step of the algorithm when it came to breaking ties, right, between multiple columns and rows with the same penalty. So I apologize if you had already watched the first video. This change actually renders the example of the last video incorrect. So if you've already seen the first video, you can just skip ahead to the example. Otherwise, just follow along as usual, like for the whole thing. Okay, so in this video, we're going to be talking about Vogel's approximation method. So this algorithm, it's a heuristic algorithm, and it's arguably the most complex in terms of steps involved of the three that we'll look at, which use a tableau. Right? So again, the goal of this algorithm is to produce a shipping policy for a transportation problem. So this algorithm tries to address the problem we saw in the last example, and that is the least cost method flaws video, where we were ultimately forced to make an unfavorable allocation. And by allocation, we mean a designation of a resource from a source location to a destination location, right? So we can think of it as a cell of the tableau, a filled out cell of the tableau, right? So that is to say, this algorithm has as its goal to ship as many items as possible from source locations to destination locations with the lowest shipping cost per item, but it tries to look ahead when doing so. So it's like the least cost method, where it wants to exploit low shipping costs as much as possible, but it does so in a bit more of an intelligent kind of way. So we'll talk more about what it means for this algorithm to look ahead later. All right, so here are the steps of the algorithm. For each row and column in the tableau containing more than one not crossed out cell, we compute the absolute difference between that row's or column's lowest two shipping costs. We call this value the penalty of that row or column, and we note this value on the tableau by writing it on the side of the row or column to which it belongs. The next step is to identify the row or column with the highest penalty. For this row or column, we identify the cell with the lowest shipping cost. If there's a tie, we take the cell with the largest rim condition that isn't shared. So if we, for example, have a tie for, let's say we had row 1 having the highest penalty, and we had a tie for shipping costs in the first two cells of row 1. We differentiate, or we choose among, or we break this tie, by taking the cell, right? So both of these cells share the same row rim condition. So we then compare the column rim conditions and take the cell which has the highest column rim condition. Okay, but we could also have a situation where we don't have an individual row or column with the highest penalty. Say we have a tie among rows and columns with a certain penalty, the highest penalty. All right, so in that case, we look at all the cells contained in all of the rows and columns, and we identify the one, or we take the one that has the lowest shipping cost. Okay, so we'll see an example of this tie breaking in the problem that we'll do for this video. And if there's a tie among cells in these rows and columns with the same lowest shipping cost, we break that tie just as we had for the least cost method and take the cell with the largest minimum rim condition, right? So if you're unfamiliar with breaking ties of cells by looking at the largest minimum rim condition, you can just look back at the least cost method video. All right, so once we've selected that cell in step 2, we take the value of the cell to be the smaller of its two rim conditions, so either the row or column condition, and then we subtract this value from the other rim condition. Right, so if its column rim condition was smaller, we take the value of the cell to be its column rim condition and subtract that value from the row rim condition. Okay, step 4 is to cross out either the row or column of that cell based on which rim condition was chosen. So for the third step, we had taken the row rim condition, we cross out the row that the cell was in, whereas if we had taken the column rim condition to be the cell's value in step 3, we cross out the column the cell was in. So steps 3 and 4 are very similar to what we had seen in the previous two algorithms. So step 5 is just to repeat steps 1 to 4 for all not crossed out cells until a single cell remains. And because we had made the assumption that the total supply is equal to the total demand, for that single cell we should have its rim conditions be the same, we just take the value of that value to be the value of the cell, and the algorithm terminates. So we're going to see this algorithm in action in the same problem that we had used for the previous two videos. You know, the problem with the 3 Apple stores in Hamilton County and the 3 distribution centers in Ohio, needing to supply them with the new 2020 MacBook Air. Alright, so I've gone ahead. Oh, I thought I filled out this tableau already. So let's fill out this tableau with that information. Okay, so 3 stores, stores 1, 2, and 3 require 40, 50, and 60 MacBooks respectively. 40, 50, 60. Distribution centers 1, 2, 3 have 70, 30, and 50 MacBooks in stock respectively. Okay, and then what's left as far as setup goes are the shipping costs. So distribution center 1 to send to stores 1, 2, and 3 is $2, $4, and $2 per MacBook respectively. So 2, 4, 2. For distribution center 2, it costs the same $3 per MacBook. And then distribution center 3 to ship to stores 1, 2, and 3 is $1, $2, and $3. Okay, so now the setup is complete. Let's use Vogel's approximation method to find a shipping policy. Alright, so we compute, right, step 1 is to look at each row and column containing more than one not crossed out cell and compute that row's or column's penalty. Right, so we identify, so we could start with the first row, identify the lowest 2 shipping costs in that row, right, which is 1 and 2. We then compute the absolute difference, which is just the absolute value of one minus the other, right? So we could, you know, take or subtract the smaller from the larger and not have to worry about absolute values at all in that case, because we know that'll be positive, right? So in this case, 2 minus 1 is 1. And then we do that for each row and column, right? So lowest 2 shipping costs in this row, 2 and 3, right? Absolute difference is 1. Lowest 2 shipping costs in this last row, 2 and 3. Therefore, the absolute difference of those in penalty of this row is 1. And we do the same thing for the columns. Lowest 2 shipping costs are 2 and 2. So a shipping cost can count more than once if it appears in more than one cell of a row or column. So that's the case here. So we get 0 as the penalty for this column. The lowest 2 shipping costs for this second column are 3 and 3. Absolute difference is 0 then. Lowest 2 shipping costs in this last column is 1 and 2. So the absolute difference and thus the penalty of this column is 1. Right? Okay, so we're still, okay. Right, so that's step 1. So we wrote those values next to the rows and columns to which they belonged. And then we identify the row or column with the highest penalty. As you can clearly see, we have a tie. Each of these rows has a penalty of 1, and this column has a penalty of 1. So, in the case, if there's a tie between multiple rows and columns, we take the cell with the lowest shipping costs from these rows and columns. So this is different from the statement of the second step of this algorithm in the previous video, right? So I'm not going to reiterate what that was because I want you guys to remember this, all right? So just bear in mind that this is what we need to do. So we look at all the cells in the tied rows and columns, which are actually all cells of the tableau because these 3 rows span all cells of the tableau. And we look for the cell with the lowest shipping costs, which is this one. So there's only one with the shipping cost of 1. Okay, so that's the cell that we select for step 2. Step 3 is, for this cell, we look at its 2 rim conditions, take its value to be the smaller of the 2, and then subtract that from the other rim condition. Okay? Step 4 is to then cross out either the row or column of that cell based on which rim condition was chosen. We chose the row rim condition, so we cross out the row. Okay? And step 5 is to check whether or not there's only one cell remaining. If not, we repeat the algorithm until that's the case. Okay, so we start back up at step 1, right? So we recompute the penalties for all rows and columns with more than 2 not crossed out cells, right? So The penalties of these two rows won't change because they contain the same cells, but the penalties of these three columns will change because now their cells have changed, right? So we look at the first column and we look at its lowest two shipping costs, which are 2 and 4, which are the only two shipping costs, right? We compute the absolute difference between 2 and 4, which we can find by just subtracting the smaller from the larger, and that's 2. We do the same for the second column. Lowest two shipping costs are 3 and 3. Absolute difference between those is 0. And then the lowest two shipping costs for the third column are 2 and 3. Absolute difference between those is 1. Okay? Alright, so we have a clear winner here. So this column has the highest penalty, right? So this is still part of step 2. Right? So step 1 was to compute those penalties. Step 2 is to identify the row or column with the highest penalty, which we did, and then look within this row or column and identify the cell with the lowest shipping cost. Right? So in this case, this cell has the lowest shipping cost of this column, which had the highest penalty. Right? And then we proceed to step 3, which says to take the value of this cell to be the lower or the smaller of its two rim conditions, which in this case is 60, and then subtract that value from its other rim condition. Okay, and then step 4 is to cross out either the row or column based on which rim condition was chosen. It was the row rim condition that we took for the value of this cell, so we cross out the row that cell was in. Alright, and then we repeat that procedure since we don't have only one not crossed out cell remaining. Alright, so in this situation, there's only one row there's only one row that has more than 2 not crossed out cells. The other 2 rows have all of their cells crossed out. And there are no columns with more than 2 crossed out cells. So, yeah. We only have to compute the penalty of this row, and there's really no point in computing the penalty because the penalty is used to select a row from which we'll then pick a cell. Right? So, since there's only one row that satisfy the criteria to be looked at, which is having more than 2 not crossed out cells, we don't have to compute penalties anymore at this point. Alright? So we can just automatically skip to step 2 and look for the cell in that row, that only row remaining with more than 2 not crossed out cells, that has the lowest shipping. Alright? So that would be this cell. We take its value to be the lower or the smaller of its 2 rim conditions, subtract that value from the other rim condition, and then cross out the column of that cell since we had taken its column rim condition. And then since we still have more than one not crossed out cell, right, we repeat the procedure. Right? And again, we only consider this row because there are no other rows or columns with more than 2 not crossed out cells. We look within this row and select the cell with the lowest shipping cost, which is this one. Take its value to be the lower or the smaller of its 2 rim conditions, which is 30. Subtract that value from the other rim condition, and then cross out the column of that cell since we took its column rim condition. And then now at step 5 of this iteration, we only have one not crossed out cell remaining. Of course, its 2 rim conditions are the same value. We take that value to be the value of the cell, and the algorithm terminates. Okay, so this is the shipping policy we end up with. Right, distribution center 3 sends 40 MacBook Airs to store 1, 10 MacBook Airs to store 2, distribution center 2 sends 30 MacBook Airs to store 2, and then distribution center 1 sends 10 MacBook Airs to store 2, and 60 MacBook Airs to store 3. Okay, so the total shipping cost of this shipping policy is the following. We can compute by looking at the shipping costs and the amounts, the allocations. So we shipped 40 MacBook Airs at a cost of $1 each, 10 MacBook Airs at a cost of $2 each, 30 MacBook Airs at a cost of $3 each, which results, this is what this results in as total cost, as I guess contributing to total cost. 10 MacBook Airs at a cost of $4 each, and 60 MacBook Airs at a cost of $2 each. Right? So this sum is equal to the total shipping cost. So this is 100, so 220, and then this would be 310. Okay, right. So I actually have Vogel's approximation method gave a shipping cost of total shipping cost of $310, and from the least cost method, from the least cost method video, and the same transportation problem, we got a total shipping cost of $310, and lastly, for the northwest corner method, we got a total shipping cost of, I think it was $440. Okay. It was certainly greater than these two, right? All right, so Vogel's approximation method, right? It can be thought of as an improved version of the least cost method. This is due to the fact that this method will look one step further when considering lowest shipping costs, trying to see what consequence, called the penalty, might follow, right? So the penalty just represents, I guess, the potential consequences, right, to the shipping cost for not choosing the lowest shipping cost of that row or column. So if there's a high penalty, that means that even though the shipping cost might not be the lowest, we may pay a higher price in not selecting the lowest shipping cost from that row or column later. All right. So, I mean, you get the feel for that, or that'll make more sense as you do more examples. However, the Vogel's approximation method is still not optimal. It's not guaranteed to give you an optimal solution. And it's slower to carry out than the least cost method, and certainly the northwest corner method. So it's just this cost-benefit analysis, when using these algorithms, So just, have that in mind. Like, this may be better, but you do need to consider, like, for practical applications, the time it would take to actually compute this and get that better solution. So it may not always be worth it. All right, so in the next lecture, we'll discuss ways to improve shipping policies that we would obtain from any of these three algorithms that we've looked at: Vogel's approximation method, least cost method, or northwest corner method. All right, bye.